Hello everyone, welcome to the dynamic programming section. So in this section we'll understand how to solve a dynamic programming problem, right? So before that we'll see that what are dynamic programming problems, and of course we'll start from the basics, right? Because we have all types of students here. We'll start from very basic and we'll go till very advanced, right? And what I believe is that in dynamic programming you do not need much theory, right? Of course theory is important, but only theory won't do the part. So I have decided to solve these 26 problems from AdCoder Educational Dynamic Programming Contest, right? So we'll solve all these problems one by one, and these problems like contains different types of dynamic programming theories there are, right? So there will be a common thing in all these problems, that would be a recursive relation, right? And we'll solve these problems one by one. It has all types of difficulty levels and different types of solutions, right? And also guys, I'll try to code all these problems in both the ways, right? So we'll solve most the problems in both the tabulation form and the memorization form, right? We'll try both bottom up and top down approach basically. So first of all, let us understand these terms: bottom up, top down, tabulation, memorization, and optimal substructure, and other terms, right? So let's come back and let's start with the basic introduction to dynamic programming, right? So in dynamic programming, what happens is these types of problems are those problems which involve maximizing or minimizing some particular subsets, right? So it's like you have all these options. Which option is the best one? Like, tell me which is the best option basically. Out of all the options, we have to choose the best option and return ourselves, right? And also, yeah, so there will be steps when we'll solve all these dynamic programming problems, right? So I think 26 really good problems are more than enough if you want to understand what is dynamic programming and how does it work, right? So that's why I'm taking all these problems one by one. So first step is, what we'll do is we'll form a state, right? So forming a state is the most important part in any dynamic programming problem. You should have a state, right? What's a state? We'll generally define it as f of some variables, right? X comma y comma z and so on. It can be many, right? If it is f of x only, that means it's a one dimensional dp because only one variable is there. If it is f of x comma y, then it's a 2D dp, right? Because there are two variable states. If it's f of x comma y comma z, and all x, y, and z are independent variables, they do not depend on each other, then it's a 3D dp and so on, right? So we can have multi-dimensional dps. And guys, yes, in the this dynamic programming playlist, we can say, I'll firstly we'll understand what is DP. We'll understand some basic terms of DP. Then we'll simply move on to solving all those 26 problems. After solving those problems, you'll get a good idea of what is dynamic programming and where it can be used. After that, we'll like solve some classical problems. Otherwise, you can solve the classical problems yourself because those 26 problems are really good, right? And yeah, so after that we'll move on to some certain topics of dynamic programming like DP with bit mask, right? And SOSDP and other stuffs, which are a little advanced part. But yes, we'll start with a basic introduction to DP and some easy problems, right? So the first step to solving a dynamic programming problem is to form a state, right? So here we are forming a state which is f of x comma y comma something, right? And the second step will be is like finding the recursive relation, that if I have a state of f of something, then that state is dependent on how many state, or if it is dependent on some limited number of states, then how is it dependent? Is it a summation of all the state, or a multiplication of all the state, or minimum of all the states, right? So it's the second is forming a recursive relation. Why recursive? Because f of something will call f of something only, right? Only the variables will change. I'll give you an example, do not worry. Forming a recursive relation. So guys, these three parts will be common in all the dynamic programming problems. Generally, dynamic programming is actually optimizing a recursive relation basically, right? So we have to optimize a recursive relation by using some different tips and tricks. Cool. Second is forming a recursive relation. For example, guys, the basic example that we always take is a Fibonacci numbers example. Fibonacci number, right? Which is how is the Fibonacci series defined? It is f of n is equals to f of n minus 1 plus f of n minus 2, right? As you can see, this is a state. What is a state? F of n. So how will it define this state? That f of n is equals to, f of n represents the nth Fibonacci number. So this is a normal definition of a state. Sometimes it can be f of ij, right? That f of ij represents something in terms of I and j. The second step was forming a recursive relation that f of n is equals to f of n minus 1 plus f of n minus 2. Normal Fibonacci number, right? So this part, guys, this part is called, the second part, it is also called optimal substructure, right? So what does optimal substructure means? What does optimal means? Optimal means not less, not more, like optimum, right? So here you can easily see that if I've defined a recursive relation which is f of n is equals to f of n minus 1 plus f of n minus 2, then only these two terms are needed, right? I'm not finding any third term here and not doing anything with it. So I'm not taking some extra terms, and I'm also including the terms that I need. So it's not minimum and it's not maximum, it's optimal, right? Only the things that we need. We are not performing any extra work here. We are only going over 2 back nodes, not 3 back nodes or 4 back nodes. So that's why optimal word is used here. We should have an optimal recursive relation. And substructure, or it's also called subproblem, optimal subproblems. So that's not tough to understand because f of n depends on n minus 1 and f of n minus 2. Similarly, guys, f of n minus will be dependent on f of n minus 2 and f of n minus 3, right? So that's what a substructure or a subproblem means, that I have a problem, it's divided into subproblems, then that subproblem is itself a problem, and it is further divided into subproblems. So I'm just giving you a basic example of Fibonacci numbers. Let's say I want to find out Fibonacci number of 6. This is dependent of f of 5 and also f of 4. Now f of 5 is dependent on f of 4 because now f of 5 is again itself a problem, right? Now f of 4 is f of 3 and f of 2. Now f of 4 is dependent on f of 3 and f of 2. So right now I just want you to understand these terms, optimal substructure, and because I overlapping subproblems. So there is a third term called overlapping subproblems. I'll explain you, do not worry. And yeah, f of 2 and f of 1, because I'll be using those terms again and again, so I want you to understand them, right? So we don't know, so we know what is f of 1 and f of 2, right? So what are f of 1 and f of 2? These will be called base cases. Base cases, that means these are not a problem, I know their solutions. So if I know what f of 1 and f of 2 represents, I do not have to divide it into further recursive relations because I simply have those answers, right? So f of 3 is f of 2 and f of 1, right? So you can easily see that all the leaf nodes in this tree, f2, f1, f2, 2, 2, 1, 2, 1 and 2, right? So all these are the base cases because they cannot be further divided down as I know their values. So for in a Fibonacci number, first two terms are 1 and 1, both are 1s, right? Great. So f of 1 is 1 and f of 2 is also 1. Cool, guys. So I hope you understood what is optimal substructure, right? I'm not making a third call here to f of 1 here and not using it, right? So it should be optimal. It should not be more, it should not be less. It should contain all the things that I need. Great. So now let's move on to the third point, guys. So always remember, I will only be performing these 3 steps again and again in all the 26 problems, right? So this is kind of a definition video basically for dynamic programming. Yeah. What's the third part? Third part is called memoization or tabulation or overlapping subproblems, right? So let's write overlapping subproblems. So I'll just code something out and you'll understand this, do not worry. Yeah, so we have overlapping subproblems in dynamic programming. So what does overlapping subproblem mean? That if I want to calculate f of 4, right? So in f of 6, f of 4 is being called here and f of 4 is also being called here, right? So it means that if Fibonacci 4 is being like found once, right? If it is being found once, if I'm going in the subtree of f of 4 here, then I do not need to go in the subtree of f of 4 here. Why? Because I've already find out what is f of 4, which is Fibonacci of 4. If I've already found that out, then why should I calculate it again? Why should I traverse in all this subtree and go to the base cases and then add them and come back? I can't do that, right? So that's what overlapping subproblems mean, that these two subproblems are overlapping. They are the same subproblems, right? You'll understand more about this when we'll be solving knapsack problem. Also, yeah, I'll code it out a little bit and then you'll understand this in more detail. So what is overlapping subproblems, guys? Overlapping subproblems mean that there are some subproblems which are repeating. If they are repeating, don't calculate them again. Find them once, store them, and when the next call is being done on them, just simply return the value, right? So in the third part, we have overlapping subproblems, repeating subproblems, right? So how to solve these repeating subproblems? There are two approaches. The first is called tabulation and the second is called memoization, right? So what are the differences between tabulation and memoization, guys? So tabulation is a table form, right? So we have a table, we have already have a static table, fixed size table, fixed size, static, right? And we are filling it. We are filling the rows and columns of it by using another rows and columns which are already being filled, right? And what is memoization, guys? Memoization is that if you have calculated state once and if I'm going on it again, so in tabulation we cannot go to any state again. Why? Because it's like a table. So in a table, all the cells are unique, right? I comma j are unique in a table, right? Because we'll be moving like for loop wise, row wise again, and we'll move to all the columns one by one. So we will not go to any state twice in tabulation. Not go to any state twice, right? But in memoization, we don't, because we are forming a recursive relation. We will write a recursive function. That recursive function, let's talk about this. We'll call f of 6, f of 6 will call f of 5, then f of 4. F of 5 will then again call f of 4 and f of 3. So here we can see f of 4 is being called twice, right? So to avoid calculation twice, to avoid all these recursive functions twice, then what we'll do is we'll simply use memoization. That means it's kind of like visited array. If you have already visited it, then don't visit it again, right? So it is saving and reusing. Or so here we'll have a memo pad, right? So what's a memo pad? It's a you can take a map, you can take a array, whatever you want. So we'll fill that array or that map with something which is kind of not in the answer, right? So if I want to find out Fibonacci numbers, I'll fill it with -1. I'll completely fill the whole array with -1 initially, because -1 will means it's not visited. I've never been to this state. So once that state has been calculated, I'll simply apply memoization. That means I'll simply store that answer in the memo pad. So when the next time I come to that recursive relation, I'll simply check that if the answer has been calculated in the memo pad, that means if memo of that particular n is not equal to -1, simply return it, because I have already calculated it and saved it. Cool. That's about memoization. In the next video, we'll like code both the ways. Yeah. So I have those 26 head coder problems. I'll code all these problems both the ways by using tabulation and memoization both. Cool, guys. And great. So in the next part, we'll understand what is how to differentiate between tabulation and memoization in detail. Right. Cool. Thank you, guys. In the next part. So welcome everyone. So in this tutorial, we will see when to use tabulation and how to use memoization and how does all of this work by coding it a little bit. Cool. So let me quickly code this Fibonacci numbers part using memoization first, right? So let's write a normal recursive relation that we have defined in the second part over here, which is f of n is equals to f of n minus 1 plus f of n minus 2, right? So here what I'll do is I'll simply say cout. Let's write a function which will give me Fibonacci numbers. Let's pass 6 to it. That means it will give me the 6th Fibonacci number. Cool. So void, I hope the font is good. So it is fib, not void, it will be integer type, it will return me an int. So here I'll take it as an n, the nth Fibonacci number. So what if n is less than equal to 2, return 1, right? So guys, these are the base cases. If it is n is 1 or 2, it will return 1. And the Fibonacci of 0 will never be called. Why? Because if I come on Fibonacci of 3, it will only call 1 and 2, and 1 and 2 will never call what's behind them, because they will come in the base case, right? Otherwise what I'll do is I'll simply return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Cool guys, let's build this. So what's the 6th Fibonacci number? It is 8 in this case. So it is 1 1, then 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, and 5 plus 3 is 8. So it's the 6th Fibonacci number, right? Now guys, I just want to count that how many times has this being called, right? This function called fib is being called. So I've just added a count there, and I just want to count that how many times is this being called, right? So as we can see, to just find 6 Fibonacci numbers, the recursion is being called 15 times. This function is being formed 15 times. Why? Because let's come back here. So when I call f of 6, it's called 5 and 4, then 5 again calls 4 and 3, then 4 again calls 3 and 2, right? So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So we can see we have 15 states over here in this recursive relation, right? So that's what we want to optimize. We want to optimize this recursive relation by applying memoization in this case, right? What is memoization? That if f of n is being like, if it is calculated once, then please don't calculate it again. So how do we do that? So firstly, what we'll simply say is, let's take an array, and yeah, let me take it a big array. It doesn't matter. We can also take a vector guys, because that will be dynamic. So let's take a vector, right? And let's call it memo. Cool. So initially what I'll do is I'll take an n, and let's say n is 6. So if n is 6, what I'll do is I'll simply say memo dot resize, and I'll say n plus 1. Why plus 1? Because I want the numbers from 1 to 6, right? So, and I will resize the vector till n plus 1 size and fill it with minus 1 initially. I'll simply pass n to the Fibonacci number, right? Why have I defined it globally guys? Because I want to use this memo in this function, right? So here you'll understand how to use memoization. I'll give you some different ways of using it, and those are really cool ways. So here it is memo.resize n plus 1 and minus 1, and I have this cout Fibonacci of n. Cool. So this Fibonacci of n is being called. Before that I filled the memo pad, the memo vector, with minus 1, right? So it's an array basically of length n plus 1 filled with minus 1 initially, right? So what I'll do is guys, I'll simply say if memo of n is not equals to minus 1. What does this mean? If it is not equal to minus 1, I'll simply return memo of n. That means this is the memoization part, right? But guys, yeah, so before this, let me have the base case with the count, right? So here is the memoization part, and here is the recursive relation. So this is what it is overlapping subproblems, and this is what it means, optimal substructure, right? Now guys, memo of n will always be equal to minus 1, because we are never filling memo of n, right? So what we'll do here is, whenever we are returning these two terms, whenever we are returning the Fibonacci of n, so here we will simply save it. So what we'll do is we will say memo of n is equal to Fibonacci of n minus 1 plus n minus 1. Now it's become so easy, right? If memo of n is not called, that means if it is not filled, then it will simply call this recursive relation. It will fill that memo pad for that nth part, the nth term of Fibonacci, and it will return that value after saving it. So when the next time I come to the same n, right, it will not call the recursive relation. It will never reach the line number 19. It will simply return back from line number 17. Why? Because now the memo n is not equal to -1, because the previous call to the same n, I filled it while returning it, right? So let me build this. See, the calls have been reduced to 9, right? So here we can see there's a lot of optimization happening, right? So let's say let me simply ignore the memoization part and let me build it for n equals to 10, the 10th Fibonacci number. So here we can see we have this 59 and the calls being made are 109. So when I apply memoization, no state will be calculated twice. So how many yeah, so for 10, how many times now it is being called? 17 times only, and earlier it was being called 109, right? So whenever, so this count is actually for a state whenever it is being called twice. Cool. So here you can see the difference, guys. So let's talk about n equals to 20. Here we can see that this is the value of n equals to 20, and only 37 times. So it is always less than 2n, right? So only 37 times this function is being called. But if I remove the memoization part, here we can see that how many times it is being called? 13,529. See the difference, 13,529 and 37. In just 37 calls we are giving the same answer, where earlier without memoization the same answer was being formed in 13,529 calls. So isn't that great, guys? So we have optimized the Fibonacci number part, right? So this tutorial was only for the beginners who do not understand what is tabulation and memoization. For them this is a very basic example. So let me uncomment it. Great. Now coming on to the next part, which is yeah, tabulation, right? So the memoization is done. Now let's do tabulation. So in tabulation, as I said, we'll already have a fixed array and we'll be using for loops instead of recursive relations, right? So let's say n equals to 20 and I want to find out this what is Fibonacci of 20. So what I'll do is I'll simply say n plus 1. I'll simply fill it. So in the tabulation form, I'll simply fill the base cases first. So Fibonacci of 1 is equals to Fibonacci of 2 is equals to 1. Cool, the base cases are done. Now 1 and 2 is filled. Now I'll start from 3. I'll go till n. And what I'll do is I'll simply say Fibonacci of I is equals to Fibonacci of I minus 1 plus Fibonacci of I minus 2. Cool, guys. So why will this work? It will work because I started from I equals to 3. So in the first iteration, Fibonacci of 3 is equals to Fibonacci of 2 plus 1, and 2 plus 1 has already been filled. So now Fibonacci of 3 is being filled, right? Now I'll do an I plus plus. So I is on 4. So when it is Fibonacci of 4, it is equals to Fibonacci of 3 plus Fibonacci of 2, which are already being filled, right? Because when I came to 4, when I was equals to 4, then it has already calculated I equals to 3 and I equals to 2 and I equals to 1. So if I am on I equals to 10, that means from 1 to 9 Fibonacci has already been filled, right? So here we will exactly take n iterations, right? 2 iterations over here and n minus 2 iterations over here, right? Here we won't have 2n complexity. But yes, the tabulation approach is a little trickier to code, right? Because here we use only for loops. Here we have to like use these for loops in a specific manner. Sometimes we have to use opposite for loops, sometimes we have to use forward for loops, right? And here we have to worry about out of index things, right? We have to like apply some conditions in tabulation approach. So it's kind of a little trickier, but yeah, this is like it's trickier, but it's not that tough, right? If we solve all those 26 problems and we'll use both top down and bottom up approaches, then it will become easier. But if you are a beginner or even an intermediate, then I would suggest you to use the top down approach first, because top down approach will give you the logic building part. It will like make you understand how to write recursive relations, how to write dynamic programming recursive relations, and then we don't have to do anything, just write a normal recursive relation and apply memoization, right? So let's say if it was int I and int m, let's say this was a 2D TP part, so here I would have taken memo n and m, right? Memo n and m, and so on, right? So if I have two states, then I have to like memoize it in a 2D table, in a 2D memo pad, right? So we'll see, we'll keep on doing it whenever it comes to us in those 26 problems, right? But I hope you understood how to do the tabulation part and how to do the memoization part. So thank you everyone, see you in the next part. Hello everyone, welcome back. And in this lecture we'll understand how is recursion the most important, it plays a very vital role in dynamic programming. So basically dynamic programming, which is DP, is equal to recursion plus optimization, right? So if we have a good recursive approach for any problem, then we can easily convert that solution into a dynamic programming solution, because every dynamic programming solution, I'm just mark my words, every dynamic programming solution has a recursive approach, right? So every dynamic programming solution will have a recursive solution inside it, which will be further optimized. So DP is nothing but recursion plus optimization, right? So if you face any of the dynamic programming problems, of course the course is going to begin and you will face lots of dynamic programming problems, right? So what I will suggest is, in the for the beginners, for any of the dynamic programming problem, just write a simple recursion, whatever recursion you can write, a very easy simple recursion about it. And then after writing a good recursive solution, because we know recursive solutions takes time and recursive solutions are very exponential, right? They take a lot of time, as we have seen in the Fibonacci series and other as well. And also I have a good question for you over here, which I'll be coding in recursion, and then we'll see how it can be optimized, right? So every DP solution is nothing but recursion plus optimization. So for any of the problem you face in dynamic programming, try to write a recursive solution. The more stronger you are in recursion, the more stronger you will get in dynamic programming, right? So write a recursive solution. If you're able to find out the correct answer of it by using recursion, then nothing but just optimize it. And how to optimize it, I've already shared. It is memoization plus, you can use memoization, you can use tabulation, whatever you want, right? But right now let's focus on the recursive part and not the optimization part. Cool. So I have a problem with you that I want to share. It is this: the number of ways. It's a very standard problem, and there's a special thing you will realize in this, and you'll understand why do we read about some sequences, right? Why are some sequences very famous, like Catalan numbers, others, Fibonacci numbers, right? So firstly, number of ways to fill an array with zeros and ones such that there are no consecutive ones. Yep. So so as I said, if you are struggling with any other DP problems, if you're a beginner, a very, yeah. So how to begin with this problem, how to solve this problem? Just write a recursive solution. Don't think of anything else, just write a recursive solution. Think about as I've already explained this, right? We need to firstly think of a state, right? What is the state that I want to take? Like, what is the state? State represents, let's say you write some function called int fun, and fun is x comma y comma z, let's say some random. So this fun x comma y comma z is a state, right? It will depend on other states, which is x comma f, which is nothing but fun x minus 1 y comma z into 2, something like this, right? So it will depend on other states. So initially we need to decide a state, like what state can I use, can I take, and after deciding that state, we have to code that state recursively, nothing else, right? And of course we'll have a base case which will return me the answer, right? So let's find a state for this answer. before that, let's understand this with an example. So let's say I have an array of length 3. Cool. And I have to fill it with zeros and ones such that there are no consecutive ones. So how many ways are there? So let's say if I come on the first place, in the first location, what can I fill? So this will be more or less like a tree, right? So let me make a tree instead. So in the first index, what I have is either I can place 0 or I can place 1, right? So if I place 0 in the first index, in the second index, so this is first, right? So every depth of this tree is a index, right? So in this second index, so this is the first index, right? And my array's length is 3 right now. So let's say n is equals to 3, the length of the array. So if in the first place I have kept 0, so we'll figure out about 1 later. Let's talk about 0 first. So what numbers can I place in the second place? I can place 0 as well as 1, correct? Because the only condition is that there are no consecutive ones. So if I place 0 in the second place, in the third place I can place 0 as well as 1. But if I placed 1 in the second place, I can only place 0 in the third place, right? So what does this particular recursion, this is recursion call, right? This is a tree going. So what does this represent? This represents 0 0 0 is a valid way because there are no consecutive ones. This represents the second one, which is this path. It represents 0 0 1, cool, again a valid way. Third represents 0 1 0, right? Now let's talk about if I'm placing 1 on the index 0, right? If I place 1 on the index 0, I can only place 0 on index 2, right? So this is on index 1, this is on index 2, and what can I place on index 3? I can place both zeros and ones, right? So yeah, again, so this is 1 0 0 and this is 1 0 1, right? So how many number of ways are there to place some to fill an array with zeros and ones as there are no consecutive ones? Nothing but 5 number of ways. I hope you understood this part, like how is the recursion being formed, right? That if okay, so basically let's write a recursive function. I'm going slow here because I want you to understand this part. This is the most important part, right? Forming a state, a recursive state, which will depend on other states, that is a different thing. That is called optimal substructure. We have already heard about it. But right now, we will just see what state can I make, right? So let's say I'm starting from index 0. I'm trying to place zeros and ones and zeros and ones again and again. So I will say, let's say f of let's say index. Cool. So f of index will represent number of ways of forming the answer, right? Okay, let's say number of ways of filling the array with the zeros and ones such that there are no consecutive ones if I place 0, right, and ones at index I. Cool. So okay, let me go again over this. So this is f of index means I'm actually taking f of index equal to whether I'll place 0 or 1 on this index and tell me the number of ways from here till the end of the array, right? So basically, okay, so initially what is the final answer? The final answer is nothing but f of 0, or instead let's say f of 1. We are considering 1 based indexing over here, right? So if I have an array, let's say it's starting from 1, f of 1 is equals to the complete answer, right? Because f of 1 will tell what is the answer if I place either 0 or 1 from 1 to n, right? Similarly, f of I means the answer to fill the array, the number of ways to fill the array if I place 0 or 1 on index I and the answer from I to index n. Cool. Okay, so let's try to write a recursive solution and then I think it will be more clear, right? So let's go. Okay, so this is nothing but simple snippet. So let's cool. And now what we'll do is we'll simply write a function. Let's call it fun, and I'll just see out this fun, right? And this fun will be our function, which will give us the number of ways to fill this particular array, right? Let me just remove this once. Cool. So as I said, I'll be taking index initially. So let's pass index as 1 initially, right? And also let's pass n so that the function knows where to stop, right? So let's say n is equals to 5 right now. So we have an array of length 5 and we want to find out the number of ways of doing so, right? And finally, okay, we will see that later. There are other things that will come into this function, but we'll see that later, right? So I have an index and I have n. What is n? N is the length till which I have to go. So I'm starting from index equals to 1. Cool. So at a particular index, what I can do is I can either place at a particular index, what I can do is either I can place 0, either place 0 here, and the second is or place 1 here, right? This is what I can do at a particular index, right? So as you can see, guys, I'm not taking an array, I'm not actually formulating an array, I'm just visualizing it, that if I place 1 over here, how my answer depends on the further index. If I place 0 here, how my answer depends on the further index, right? So cool, let's take answer. Initially, let's say answer is equals to 0. So what does this fun tell us? Fun returns me this answer value, which is answer for array index to n. Number of ways of making this from index to n, that big array. Cool. So as I place 0 here, so if I will place 0 over here, right, then I can easily say that answer is equals to place whatever you want to place on the next index, right? So let's say it is equals to index plus 1 and n will be as it is. Cool. But I cannot place 1 here without knowing what is placed on the previous index. I want to know what is placed on the previous index, then only I will be able to place 1, right? Because the problem says that you can't place 2 consecutive ones. If I can't place 2 consecutive ones, then I need to know what is kept on the previous location. For that, what I'll do is I'll just take a boolean with me, right? So I'm just writing a normal recursive solution, which is, let's take a boolean which is called 1. This will tell me whether 1 is placed on the previous index or not in the recursive call, right? Because as you can see, if 1 is placed on the previous recursive call, then I can only place 0 over here, right? I cannot place 1 again. But if 0 is placed on the recursive call, I can place 0 as well as 1, right? So let's come back over here and I have a boolean value 1. Okay, so tell me, just think about it, what will be the value, the third value that I should pass in this function when I'm placing 0? It should be false. Why false? Because this one boolean represents whether, let me write it, 1 represents whether previous index is 1. Cool. So if I'm placing 0 over here, this is my case for 0, right? That means I'll just pass false to it, that I have placed 0 over here, it's not 1. So 1 will be false, right? And when can I place 1 over here? I can only place 1 over here when 1 is equals to false, right? So okay, let me rename this. Previous, let's call it previous one. Cool. So if previous one is false, that means if I have not placed 1 before, then I can place 1 here, right? So answer will be equal to, and this is index plus 1 comma n comma true. Let's call it true. Why am I calling it true? Because now I'm placing 1 over here. This is the case where I place 1, and when do I place 1? There is only one condition, that there should not be a previous one in the previous recursive condition, right? So this is simple recursion, right? It's just 5 lines if I remove comments and spaces. Cool. This is for 0. I'm placing 0 because 0 can be placed without any restrictions, but 1 will be placed with a restriction, which is there should be no previous ones. And initially what I'll do is I'll pass false over here, which is, you can keep any, either 0 or 1 on the first index, because we are starting from the first index, we are just passing false initially. Cool. And yeah, let's build this. Okay, so why won't this work? Why am I getting some errors? Because we all know, yeah, segmentation fault. So when do we get segmentation fault? When there's a stack overflow. What is a stack overflow? When we go over the recursion and the stack builds up, right? If there is no base case, then it will keep on going forever. The index will keep on increasing by one. It will never know when to stop and return, right? So let's write a base case. So if index is equal to n plus 1, because till n I have placed, right, either zeros or ones or zeros or ones. So when index starts from 1, goes to 2, 3, 4, and when it goes to 5, again it tries to place zeros and ones on 5 as well. When it reaches n plus 1, 5 plus 1, which is 6, right? So in this case, when it will reach 6, then I want it to return back, right? And what should it return? It will return as 1. Why will it return as 1? Because I'm keeping zeros and ones from the first index, right? All those index have zeros and ones. So if all those index have zeros and ones, this is a proper valid arrangement that I want. So if it is a valid arrangement, then it will return as 1, right? That means it is a valid arrangement. For example, let's come back here. In this case, what happens is I place 0, then again I place 0, and then again I place 0. Afterwards, what happens is this calls the next index, and of course we can't go above n. So what I say, right now I'm on n plus 1. That means this is a valid arrangement. So if this is a valid arrangement, just return me 1, that I have got one valid arrangement from it, right? So I'll just simply return 1 over there. So this is a base case. I'm going slow, I'm repeating a lot of things here because I want you to focus on the recursion part, right? So let me build it again and let's see if it fails. So as we can see, it did not fail. It gave me 13, right? So this is for 5. As I said, let's try it for 3. Cool. So for 3, the answer is 5. Now I just want you to see a pattern over here, and then you will easily understand it yourself. The pattern, you can easily see it. Yeah, cool. What I'll do is I'll run I from, let's say, 1, and let's say it goes till 10, right? And I'll just pass I as the value of n over here. What is n? N is the length of the array that right now I'm thinking about. Cool. So if n is the length of the array that I'm thinking about, so I'm just passing it as I. So firstly it will tell the answer for 1 array length, then it will tell the answer for 2 array length, and so on till 10th. Cool. So I'm passing this n as I, which is a variable. Let's build this. Cool. So guys, can you here see that there is a pattern involved in this situation? 2, 3, 5, 8, 13, 21, 34. Do you remember this to be any of the series that you have heard about? Right. So this is a Fibonacci series, right? So as we know, Fibonacci series starts from 1, then 1, then 1 plus 1 is 2, then 1 plus 2 is 3, and so on, right? 5 and 8 and so on, right? So again, here we are getting answers as Fibonacci series. So for a particular I, let's say if I is equals to 1, answer equals to 2. So here we can say that the answer for this series equals to Fibonacci of n plus 2, right? Because if I is equals to 1, answer is equals to 2. If I equals to 2, answer equals to 3. If I equals to 3, answer is equals to 5. Cool. As you can easily see. So in short, the answer is equals to nothing but Fibonacci of n plus 2, right? So this is a very standard type of question, and by this problem we realize that all those series are kind of related, right? So we would have never thought that this series would this particular arrangement would give us Fibonacci numbers as the answers, right? So yeah, so here I'll leave you with a problem, which is if the answer is equals to Fibonacci numbers, then why was the recursive relation that I formed, right? So here is the recursive relation that I formed. Let me write it also. So the relation that I formed is index comma boolean value, which is previous one, and n is the length of the array, right? And what I'll do is in the next part I want you to understand why is the recursive solution not equal to uh, something like this. Fibonacci of index is equals to Fibonacci of index plus uh, Fibonacci of index minus 1 plus Fibonacci of index minus 2. I mean the Fibonacci series, right? So just think about it, and then we will come back to it in the later section of the course, right? In the 1DDP section. So this was just about an introduction video that every dynamic programming solution will have a recursive solution as its heart, right? And cool. So we can also discuss about the complexity of this function, and this is normal recursion, right? So what will the complexity of this? The complexity of this is equals to the Fibonacci numbers. So it is 144. How are we getting 144? Because we are summing up those many ones, right? So we are going to the end of the tree, coming back, going and coming back, and just moving up and down recursively and adding all these ones. Cool. So yeah. So the time complexity of this is O of Fibonacci of n plus 1, basically O of answer, because this is a recursive solution. Now just think about it. How many parameters in this function are variables? So index is a variable. We can see that index is continuously changing, right? Is n changing, guys? N is not changing, right? So in all the recursive calls, n is constant, right? And the third variable is previous one. So either it is false or true. So there are only two values of it. So if I want to memorize it, if I want to save the answer and not call the recursion again if it is already being calculated, then how many states can I have here? I can have index, because index is changing from 1 to n, right? So index into previous ones of states. That means, sorry, index into previous ones. And what is previous ones? How many previous ones are there? Because only these these two are varying, right? So these many combinations I can have, right? So how many indexes are there? There are n indexes. And how many previous ones are there? N into 2. So I just need an array of n cross 2 to memorize this recursive solution and to bring its complexity from O of Fibonacci numbers back to linear, right? Because this is a linear series. Here we can see n into 2 is equals to linear, right? 2 into n, right? So if I want to memorize it, I can also memorize it, and then it becomes a dynamic programming solution. Hello everyone, welcome to this part, and in this again we'll understand how to find recursive solutions when there doesn't exist recursive solutions, right? So I've taken a very simple problem, the most easy problem there would be in the history of dynamic programming, which is print number of set bits for each number from 1 to n, right? For example, let's say n is equals to 10, right? So what I have to do is I have to actually see out 10 numbers, right? What are those 10 numbers? Let me just write those numbers over here. So I have numbers from 1 to 10, and we have their binaries, right? So 1's binary is 1 and 2's binary is this, 3, 4, 5, 6, 7, 8, 9. So I hope you know about binary because this is very important, right? And what I have to print? I have to print the number of set bits for each number, right? So how many set bits are there in 1? 1. What is the meaning of set bits? It is the count of ones in the binary of it. How many set bits are there in 2? 1. 3, we have 2 set bits, we have 2 ones. For 4, we have 1 set bit. 5, we have 2 set bits. Similarly, 2 set bits, 3 set bits, 1 set bit, and this is 2 set bit and again 2 set bit. So basically, I have to print this out, right? And so you all might be wondering that it's a very easy solution. You'll just head on to the code editor, run a loop from 1 to n, call a function which will give you the number of set bits, right? But what will the complexity of it if I just write, okay, let me code. Yeah, okay, I think I need to save this one. Let me save this, and let's call this no consecutive, sorry, yeah, and let me close this. So for this particular problem, you all might be wondering that what you will do is nothing but you just start your loop from 1 to n, 1 to n, whatever the value of n is, right? And what you will do is you'll just see out and you'll just write a function which will just give you how many number of set bits are there, right? And this is the most easiest brute force solution, and also you can see the complexity is not much, right? Because if I write a function which is let's say int, and let me call it return set bits, right? So what, how much complexity of this function will be? It will be log n in the worst case, right? So what you will do is you'll divide by 2 and give me the number of counts. I hope this is pretty easy for everyone. And what is the complexity of the whole code? The complexity of the whole code will be n log n. This is the most easiest part, but I want you to do it uh I want you to do something better than n log n, and not just, you know, n log n. Can you do it in n? Can you uh print me the answer in just O of n by just going over all these numbers once, like just running one loop from 1 to 10 and not calling any other function or any other thing? Think about it, right? What I'm saying that this brute force solution will take n log n time, because n for this particular array and log n for this function to return me the number of set bits. But I want you to do it in O of n complexity only, right? So O of n complexity. How can we achieve the O of n complexity in this case? So it's so for that you need to figure out a recursive solution, right? Because we know that if I'm able to find out a recursive solution which is something like this, f of I depends on some f of I only, right? Or I dash, let's say, then it can easily be computed in O of n, right? There will be recursion, we'll simply memorize it and it can easily be computed, right? How can I find out this particular recursive solution? So the answer lies in this. The answer lies in all these pairs here. So let me okay, this is a pair which is, let's say, a number is x and its pair is x into 2. You have to see the similarity between x binary and x into 2's binary, right? So do we all know about left shift operators? Let me like quickly tell you some extra knowledge. Of course this is not required, but just for we can connect to it, I mean. So what does left shift operators do? They left shift the bits by the number of digits we tell them to, right? Basically, let's say uh if I say uh 3 left shift one time, what does this mean? The binary of 3 is this, and left shift will just, what it will do is it will just shift those two digits to the left of it. Basically it will become 110. And what is 110, guys? It's nothing but 6, right? So basically, if I left shift anything, let's say x left shift 1 times, it is nothing but equal to x into 2, right? Because the value is left shifting. And what is right shifting? Right shifting is nothing but x divided by 2. So as you can easily see, if I left shift 3, sorry, if I right shift 3 by 1 time, so binary of 3 is this, and if I right shift it, then I will only be left with 1 1, and the last one will just go. What, whose binary is 1? It is 1. So you can try on these pairs. Let's take two pairs. Let's take 5 and 10. So let's say, let's do a 5 left shift 1 time. So if I'm doing left shift 1 times, I'll just apply a last 0, and this is nothing but 10, as you can see, the binary of 10. And what is 10 right shift 1 time? It is nothing but 5. Cool. So what I'll do is I'll simply form a recursive solution here, depending on the understanding that I've just formed, which is that dp of I is nothing but dp of I by 2. That means the number of bits in I, right? If I'm talking about some number I here, the number of bits in I is equals to number of bits in I by 2 plus. So here I want you to finish this by yourself. Of course I will be telling it. So let's see the relation, right? So if I have I by 2, which is, let's call it a random number. So let's say this is I by 2, So if I multiply it by 2, what does it mean? I'm left shifting it by 1, right? So basically, number of digits in I is equals to number of digits in I by 2 plus the last bit. So how do we determine the last bit, guys? What does the last bit represent? Just think about this. There's a pattern again. I just took this question for some educational perspective only, because this will tell you a lot about left shifting, right shifting divided by 2 and multiplying by 2, and the last set bits, the specialty about the last set bits. As we can see, every alternate number has the last bit set. So this is nothing but odd numbers. So every odd number will have the last bit set, right? So what I can do is I can simply say if dpi is equals to dpi by 2, because those bits are same, right? So basically if I left shift by okay, let me left shift it by, yeah, so this will be the left shifting of the particular, this is x, this is x into 2, right? And what will be the last set bit here? What will be the last set bit of the x by 2, of x into 2? It is nothing but, it will depend whether x into 2 is even or odd, right? So of course x into 2 will always be even, right? But I'm just saying that if I want to formulate this particular relation, which is dpi is equals to dpi by 2 plus odd odd I, right? What is odd I? If I is odd, it will give us 1, otherwise it will give us 0. That means the last set bit of odd, right? So this is a simple recursive relation. So let's try to fill the whole array with this. Me write. Cool. So as I said, dpi, let's fill all the dpi's over here. So for 1, what will be this solution? So dp1 is equals to dp1 by 2, which is 0, right? So for 0, let's fill 0, because we know it's a base case. Plus, is 1 odd? Yes. So what's the answer? It is 0 plus 1. Cool. So dp2 is equals to dp1, because 2 by 2 is 1, right? So dp2 is equals to dp1 plus whether it is odd or not. It's not odd, right? So how much will it be equal to? It will be equal to 1. Similarly, dp3 is equals to dp 3 by 2 is 1 plus whether 3 is odd or not. Yes, it is odd. So basically it will be 2, because dp1 we have already count, which is 1, right? So in this way we can just go once over this whole array and keep on printing the elements, right? So let me just code it very quickly. Let's say n is equals to 10. Let's say I goes from 1 till n, right? So let's have a array called dp, and let's say it is n plus 1 length. So dp0 is initially 0. Cool. So dp0 is 0, and I'm taking n plus 1 because I'm printing till n, right? So what I'll do is simply dpi is equals to dpi by 2 plus, now I by 2 means it has been left shifted, right? So I by 2 has been left shifted, and now I have to decide whether the last bit is set or not. So how can I decide? Simple. If I by 2, right? So if it is an odd number, it will give us 1. If it is an even number, then it will give me 0, right? So simply I'll just print this out, dpi, and let's build it. Cool. So 1 1 2 1 2 2 3 1 2 2, right? So as you can see, the complexity of this solution is now O of n only, and not even O of n log n, because we have simply find out some pattern in the recursive relation, and we have found out this recursive relation. This is a recursive relation, right? The dpi depends on dpi minus dpi by 2 plus I mod 2. I mod 2 is whether it is even or odd. Cool, guys. So I hope you understood this. Thank you everyone, and see you in the next part. Hello everyone, I have a small tip for you all. So the tip is very simple, that if I have so now we are beginning with lots of dynamic programming problems, and as you know, we have strict time limits, right? So I won't be coding all the problems in both the bottom up manner and the recursion plus memoization, that is the top down manner, right? So I won't be coding all the problems in both the ways. of course I will be coding all the problems, but only in one of these ways, right? Either I'll code it bottom up or I'll code it top down. I'll just decide that whichever is the tough one, I'll code it. But what I want you to do is, if you want to get the best out of this course, what you can do is you can simply try out the other approach yourself and try to submit the problems online, right? So basically what I'm saying is, if I have done the memoization plus recursion, the I've coded it recursively, then what you can do is you can try and code it in the bottom up manner, right? Because in that way it's beneficial for you only, that you will realize that there are different ways to code a same problem, right? And maybe that will help you get more familiar and more, get some deep details of the problem as well. So thank you everyone, all the best.